All right. Guess I'm just going to wait to see if more people will show up before I start coding. One thing I know that I want to address is that, excuse me, right after I shut down the stream, I realized there's a latent bug in the way I'm doing the register allocation, combined with some of the copy propagation in cases like, what's an example? Yeah, like a case like this, where you're doing a multiply and the destination is an immediate and the other one's register. In that case, I sort of steal the operand register. Like this doesn't guarantee that the operand will actually be in free register, and so after that, it's possible for the operand that I'm kind of stealing to store the destination is actually possible for that to be dead because of the stack allocation order for the registers. So what that made me realize is I should make more explicit to myself how I'm actually tracking register liveness. And I think this example shows that doing it in a pure stack style probably isn't the way to go. So my thought was I will use some sort of bitmask approach to tracking live registers, and then from there we'll basically do sort of a allocate and free register approach. So we never have to worry about that. The default allocation order will still essentially be like a stack, right? Like it will be the first unused register will be used, and so on. But hopefully it will not only solve the present issues, but it will also let us scale to more complicated situations as we expand the compiler. But yeah, so just to see where we were yesterday. So let me just generate some machine code and then disassemble it. So for this test expression, we now generate this. So you can see we do a strength reduction. We do a strength reduction for the multiply by 8. And you know, we use kind of mostly good addressing modes, although I see one issue here that I don't think there's a reason. Let me check the instruction manual. I don't think there's a reason we couldn't use the memory argument directly to div. So let's check that. Yeah, we can use an M64. So maybe that's a good little starter task to see why that's not happening before we dive in and do the register allocation tracking differently. So right now, I say emit as register, but really, let's see. Well, maybe this isn't the right long-term way to do it, but if we have a variable, past recordings. Someone's asking about past recordings. Yeah, I actually uploaded a bunch of them to YouTube yesterday. Let me paste the. I'll put the I'll put the channel link in the overall page. But you can see for now. You just go to this link. I uploaded the ones from yesterday and Friday. Okay, yeah. So basically, what I could do, although I think I should step back and figure out a more general way to do this going forward. But just as an example, I think if we did that. Any functions, definitions, etc. that won't work on some distribution of Linux. I mean, very little. I don't think I am. I think the only parts you'll find are just like some of the stuff where just for opening memory mapping the file. But you know, you can just read the string indirectly if you want. You don't have to use memory mapped I/O. But the assembly code itself, all the machine code stuff, the compiler itself, all that should be portable to any 64-bit machine, maybe even 32-bit, although it generates 64-bit code. Anyway, so yeah, let's see if that runs. Yeah, so did you see how now, rather than using a temp register, we now we now generate the right addressing mode directly. Well, 64-bit x86. I'm generating a 64-bit x86 code. Yeah. Actually, let me do... No, let's just keep that stored in a temp variable. Okay, still works. It's a little bit annoying. You have to do a lot of these things with the various variations to handle the addressing modes. Because in theory, I have to go and do the same shit for ads. Yes, the destination has to be there. But like, for example, in this case, maybe I should have a macro to do this shit. getting a little bit bifurcated. Okay, so a case that should exercise would be if we do 4 plus x right. Oh, I guess this is a bad example because let's do x plus 4. Yeah, no, it always does that, so that's probably fine. A better example maybe is x plus y. Then it's going to materialize one of them in a register and the other one, right? So one of them is going to just do a register load, and then for the other one it's going to use the right right addressing mode for the right operand. But yeah, this stuff is a little bit repetitive because you're always going to have this like, hey, is the offset less than 1 byte? Do one thing. You know what? Actually, for now, I mean, let's just assume. Let's just special case this for now so it doesn't get too out of hand. But at least assert. And I think later on, if we want to handle, well, let's see. So for 64-bit variables, that would be 128 divided by 8, which is 7 minus 3. So, I mean, that's, yeah, it's like 16 variables, I guess. Yeah, let's just leave this for now. I think probably later, if we handle the more general case where we have a lot of variables in the stack frame, I think the way we'll do that is probably be writing a macro that does some of that discrimination for us, because we're going to end up writing the same shit for every single instruction otherwise. Okay. Okay, I swear that there is something super weird. Okay. Okay. Actually, let me just replicate some of this stuff here. Let's verify that if we do subtract, we get that nice addressing mode, and we do. I think we had to do it also for multiply, right? So let's see, what if emit as register? We actually don't know. So actually, let's verify this bug. I just noticed a bug here. Because we don't handle when operand is an immediate that is not a power of 2. So I think what you want to do, because there's no version of div that takes an immediate operand, I think you want to do emit as register operand free register. So we're just using it as a temp. And then we're reusing it. So we're potentially reusing it here, but that's fine because we only really need this for the duration of the divide. And so if we do x over 2, actually x over 3, it can't be a power of 2, otherwise we're going to get a strength reduction. Yeah, so that gets put into a temp register. So rex is the local variable, which is x, and then we put that in. Oh, that's weird. That's totally not. This should be R15. What? That's super weird. So presumably it's hitting this case, right? So this is an immediate. Now the immediate is a register, in register 15. So why does... Well, clearly that thing didn't go well. So issue a move. Okay, let's not be in release mode. Okay, so we have the immediate 2, and we're being asked to put it in R15, and oh, I know. So there's a bug in this. This is interesting. How the heck is that even possible? Did I blow this? Oh, there's no rex. How the fuck did that get deleted? Oh, I see. Oh yeah, move has that weird thing where if it's doing a move to a 64-bit register, it always wants it to be... Seems really dangerous. So if I do that, it should be fine. Right, so that works. But the problem is we now have this big ass immediate, which is nasty. Like when I'm just moving something small, I don't want to have to do that. Right, so I want this one. Moving to a 64-bit register, but with... So this is B8, and this is C7. Okay. C7 with an operand extension of 0. Okay, so this other one has that weird operand encoding where you do the plus. Whereas... Well, let's see. I think that actually works. Okay, that's better. I mean, it's still doing it as a yeah, no, I think this is better. So it's doing the implicit 0 extension, which is, you know, I guess I could do is there a way to move a single byte to a R6 or to R64? Maybe not. I mean, you can obviously do the 0 extension. Maybe that's how you do it. Move CX. Well, there's no, yeah, so there's no move CX with an immediate. This is where having Fabian would be useful, because I actually don't know all the different x86 instructions and their random permutations as well as I should. But it seems like it would be, well, it would be nice if there was a way to implicitly 0 extend like a byte as you move it into a 64-bit register, but there doesn't seem to be a way. I think the closest you can get is 32-bit 0 extended to 64-bit. Oh, and this is sign extended, so that's actually something I didn't even notice, which is definitely not what we want. Or is it? Is that what we want? No, I don't think that's what we want. Maybe I should. I almost want to call this something like that, but that's not totally true either, I suppose. So move CX is here, move SX is where? For now, I'm just going to pretend it's not an issue. And at least by renaming it, I'm sort of making it obvious that it's a sign extension. Okay, this is pretty good. All right, I think I'm going to go do the register allocation crap now, rather than futzing around more with this. Oh wait, no, that was the multiply. We weren't. We were in the middle of doing this. Right, in the case we want to test with this, make sure it uses the right addressing mode. Yep. Okay. Okay, let's go and redo the register allocation. So right now, I did this thing which actually felt weird to me almost from the start, and I just sort of went with it. But I pass in this free register, and then there's a get next free register, which basically does a guarded decrement. So it starts at R15 and it will go all the way down to R8. And probably the right way to do this is just to have some global state that tracks the register. And vis-a-vis the thing I mentioned earlier, I think we're not going to have a pure stack, like a pure stack liveness kind of approach. I think we're just going to have a bit. We're just going to have like a bitmask, and so free register mask. So we basically want this to be 0, 0, 0, 0. Well, we want it to have let's see, all of these bits except for all of these bits. So this corresponds to an initial state where R8 through R15 are free. And then we will do something like this. Allocate register. So bit scan forward. So first off, assert that this is not 0. Because if it's 0, it means we have no free registers, and for now we're not doing any spilling. So that's what we're doing. And we do a bit scan forward, free register mask. What's the signature on this? I see. Something like this. Bit scan forward, cannot convert from register. Okay. Okay. And then we have a free register function. Oh yeah, this is actually not enough. We also have to clear it. So once we found one, we need to clear that bit. So let's do an assert to make sure this is not already free. So if we AND this with that mask, this should be 0. And then what we do is we put that back. Okay. Does that look right? Let's do a quick test. Okay, let's just step that in. Right, so that looks right. And then if we well, I think this will loop forever, but maybe that by itself will be an okay test. So we're trying to free 8 and the mask oh, so it's actually what the compiler warning was about, because he has completely brain-dead precedence with the bit operators. Okay, so that is looping forever, which is what I would expect. Alright, so we're going to just say that this is totally working. So now we have to go through and fix all the register allocation uses. So first off, we're going to remove all this junk. We now don't pass this down. And instead, when we need a register, well, first off, we don't need to do that. So the code also gets a lot simpler in these functions. Let's just do the parsing functions first, then we'll do the emitting functions where the work will actually happen. So this is parse term and then parse atom. Okay, it does not take 2 arguments. Right, so let's start with the adds and frees, I guess. So it no longer takes a free register, which means at any time we need to, okay, so now emit as register does not take that argument either. It will just do its own allocation. Yeah, so all of this gets really simplified. All the register crap gets pushed into the leaves of the call tree, I think. Except this one. It's a free register. Well, I guess the way to do it is if this is not already a register, let me do that. Actually, so this kind of code should be pulled into a function called allocate operand register. Which I think basically does so post condition is this thing has a register allocated. I think I called that with the wrong function because this should be called on the destination. Okay. Emit as register does not take one argument. So emit as register, we now don't take that. Does not take two arguments. Right, so that's the same deal for div, which is okay, there's no way this works, right? Move rex to rex. Oh, that's certainly a bug. So this was for multiply. Okay, so the destination is operand 1. Interesting. Okay, so right now it's variable 0, and I'm assuming this is the thing that does the mistake. So it says, hey, we want to move it to that. We emit the move. I believe that was actually correct here. Right, so that part is correct. Yeah, this is actually a mistake. Just because you say that something is moved to a register doesn't mean that that operand in general is in that register. Let me think about that. Yeah, I think that's right. Right, so the post condition of emit move to register is that the value has been moved to the specified target register. It's not that the sort of the home address, if you will, of operand has changed. That's only, I think, true here. It can do that because it's allocated the registers. Now it has laid claim to it. So that was a latent bug even in the code from yesterday. Anyway, so that was good we found that. So yeah, we emit the move to RAX, and we then do this, and then here, I think we should be fine now. So let's look at the disassembly. Right, so now this looks good. Okay, the part we haven't done is free any registers, which means that over time, while this is semantically correct, I mean, I guess I can show you what I think will happen, but if you do something like this, you're going to see that each of the sub-expressions is permanently going to allocate a register, and you're never going to get anything freed. I guess there's not enough cases here, maybe, to... So let's do something wacky like this. Right, so you can see that even though in theory I think you only need maybe 1 or 2 temp registers for this whole expression because the depth of the expression is not that great. It's mostly just sort of a left recursive chain of things that can be reduced in place. We go all the way from R8 up to R12, and that's because we don't free any registers right now. So the code is sort of semantically correct, but we never really free the lifetimes of the temp registers. So we need to fix that. So I think what we need to do is first off, let's add a type of operand that represents like a null state, just so we don't have any kind of use after free kind of issues. We're going to mark things. So once we're done with it, we're basically going to say this thing is null. And then if the operand register so if this is a register, then we have to free the register operand. Okay. Sorry, let me just check the chat. Someone's asked, Caleb is asking, I'm new to the stream, what is going on? So working on a kind of a native code compiler targeting x64, x86 64-bit. On Friday we wrote the first half of the x64 code emitter. Yesterday morning, Saturday morning, we wrote the first half or the second half of the code emitter, and then we started writing a compiler. So far, we just have simple lexer parser for an expression language, and then a code emitter. And I'm intentionally staying a while to focus on some of the code generation patterns and register allocation for expressions, because a lot of the things that will sort of be replicated for statements and function calls and all this other stuff that you consider more of a normal programming language feature, a lot of that foundation is really laid at this point, and so the rest of it I'm not too worried about. I know how to write it very easily, I think. We'll see, but yeah, so we're sort of trying to lay the right foundation for the rest of it now. So that's where we're at. And now I forgot where I was at specifically. All right, we have to have free registers. So basically what we want to do is, I think the general convention is, let's see, when the destination operand is kind of like a return value. So if you think of this in terms of almost like reference counts, we want to make sure that this thing is still alive after we return. So we're never going to free our we're never going to free this. I think what we will do in a case like this, basically when we're done with the operand, let me think. Right. There's a few cases right now where I steal the register. Like for example, and sorry, I just realized there's something I have to do before I forget, because this is a little bit subtle. There's a few cases like this where the destination steals the register from the operand, and you can get double free errors here if you're not careful. So I think what you want to do here is actually like essentially you want to make this operand null when you're done with it. Because otherwise whoever later on is going to free up this operand may free it even though the destination is now using it. So when we're transferring ownership, we have to be careful to do this. Does that make sense? We obviously have to do this for the divides as well. Oh, we don't actually do that for divides. So I guess that's one somewhat subtle case of that. Actually, I think one way we can we can actually formalize that by saying like transfer steal operand register. It's not a typo I normally make. All right. Emit, divide, constant folding with a multiply. Not sure I understand what you mean constant folding with a multiply. Okay, so let's pop the stack. So here we create new operands to store results. If we ever, once we're done, like these functions will essentially be done, then we free it. The assumption is the destination is owned by our caller, so we're never going to free the destination. So that's sort of the invariant. It's a parse term. Okay, let's see if that fixed the greedy overuse. Right, so I think that fixed it. Before you were seeing, well, actually, let's try removing these, or actually we can do it another way. We can just try doing a return here. If we do this, we should see back to using too many registers, like up to R12 for the temp registers. Yep, up to R12. If you put this back in, it should only use up to R10. And even the 10 is only, let's see. Yeah. So this is not too bad code generation, actually. And I think the register allocation is now kind of conceptually, and well, actually and conceptually clean. Does anyone have any questions about the anything we're doing here, either in terms of the code generation technique or the or maybe the register allocation stuff? This is all for expressions. In theory, register allocation for expressions is basically, I mean, aside from weirdness probably related to specific instruction architectures like x86, in theory it's pretty simple because the lifetimes are kind of nice and nested in a sort of tree shape, which is why we can do this free operand stuff very simply. We didn't have to do any fancy tracking. Why do free registers start from 8? Let's see. Right now it's mostly me making things easier for myself, but or maybe I'm not making things easier for myself. So first off, RAX and RDX are routinely destroyed by instructions like mul and div, and so you can certainly use those for you know, it's the one problem with using them for intermediate results is that you sometimes have to save and restore them into other registers. So it's just a little bit, I'm staying away from that from now. We can maybe consider it later. Actually, so and the original reason why they were contiguous range is that I was using this simple stack allocator, but now that I have something, now that I have a more general purpose allocator, actually it would be easy to do. Let's just do that. We can do something more general purpose. So let's say RCX is available. RDX is not. Well, let's just take a look at the chart here. What were we? Initialize free registers. So RCX, RDX, RVX, RSP, RVP are reserved, RSI, RDI, R8, R9, R10. Only free once. That's probably a good idea. Well, although it won't actually matter, but good catch. So yeah. Yep, it does make a difference. But anyway, you can see we're now using RCX, and the next register should be... Oh, so we are using RDX? That's a bug. Did I put that in there? Maybe there's a bug elsewhere. So after the div, so after it's emitted the div itself, it moves RAX to Is that some weird off by one thing? Because, wait, no. RDX, RDX is after RCX in the ordering. So it goes RCX, RDX, RBX. Oh. Pfft, I'm an idiot. Sorry, guys. Alright, so now it goes to RBX rather than RDX. Much better. Okay. So let's see. I'm trying to think of what the next step should be. I could either start doing statement stuff, or I could expand the repertoire of operands. So basically, right now we have local variables. We also need global variables, and we also need to prepare for... so actually, I can tell you a little bit about how Viet does his delayed code generation techniques, which is where this approach I'm outlining here is generally taken from. But he has broadly two categories of operands, and you can kind of lower between them. There's one that's higher level at the language level, so it will be something like a variable. And then there are lower level ones like frame offset and memory. So this would be like, RBP plus offset, and this would be just like address. And one reason this is really nice is, suppose you have a variable, and the variable is a struct, and then you want to do something like person.age. Essentially, you want to convert that to RBP plus person offset plus age offset. And you can do that entirely by essentially doing kind of offset math in this way, using these operand types. So I'm just trying to think about how to structure this best. So sort of the idea is that if you think about it from the low-level instruction selection point of view, really what you care about, like right here I called it variable, but really what you care about is like, is this something that I can do this MD1 type thing to? So you don't really care about the higher level thing once you're doing instruction selection. You just want to know, is this something I need to use the special addressing mode with? Let me think for a sec. Okay, so let's just say we have an address operand. Sort of, you think of like high level versus low level concepts. There's register, immediate, address, and frame offset. Maybe we remove this. We just have frame offsets. We keep this in reserve. Oh, okay. There's a bug in Visual Studio, I swear, that kills. We were looking at this yesterday. I know about, like, it's not like Emacs style undo where you can never lose your state because you can always undo the undo. But like, there's something that's causing it to get killed all the time, even when I'm not doing anything, which is terrifying. Um, because now I have all this junk. Okay, we should just have the same as before. Right. So yeah, let's add the support for global variables. I mean, this is an identifier. Yeah, I guess we can say local variable and global variable. Nope, it's definitely not that. And for now, we're just going to use kind of ordinal indices and assume that local variables start at offset 0 from the frame. Global variables start from memory address 0. And so we will keep these as local variables. These have to be 64-bit because it's 64-bit crap. And then we are going to and actually I just realized we should just unify these three cases. We're going to do the same for global variables. Okay, now we have these to worry about. Oh right, parse atom we have to fix up. Hmm. Do I do everything with rip relative addressing? Maybe I should do everything with rip relative. That's the modern thing to do, I guess. The problem is if you don't use rip relative addressing, no, I think for global variables we actually don't want 64-bit. All right. So actually, before we start doing the special case addressing mode crap, let's just do the general purpose thing, which basically always works. No, let's not do that. Okay, so if we now start swapping in some of these with like A, B's, and C's, okay, I got a bug. So I do an emit to register. Oh, I can't, I see, I can't. I have to do it as a displacement. because I'm not passing in a register, I'm passing in a let's make sure I got everything. That's D. That's D. That's D. That's D. That's D. All right. Fingers crossed. Well, we got no assert this time at least. Yes. Behold. Okay, so we now have global variables supported. Probably we should start doing statements. I mean, we could obviously fill out the repertoire of operators from just the plus, minus, multiply, divide to include the usual suspects, but that's going to be more of the same, so I don't think there's much of a point to doing that. I mean, we can certainly, we will have to do it eventually, but it's not very exciting. Instead, let's do statements. What's the end? So Angus is asking, what's the end goal? C compiler or your own language compiler? I mean, I don't know if there's an end goal. Well, there's an end goal. I think the end goal is mostly educational, which is show that, you know, how to write something completely from scratch without helper libraries, and hopefully teach about, you know, x64 low-level stuff, general compiler techniques. I'm intentionally taking a one-pass compilation technique that's I think kind of underused. You can use it to write fairly decent, like in terms of optimization, compilers that are super fast. Like once we put in statements, we should actually benchmark this to see how fast we can make it run. I would expect we can probably compile, I don't know, like 1,000,000 lines a second or something. I don't know if that's true or not, but I wouldn't be surprised if it's on that order of magnitude. So yeah, so the main goal is, I guess, more educational than practical. Although, I mean, in general, I only want to show things that are practical. I don't want to show things that are toys or don't scale to real-world problems. So, but mostly educational. All right. Statements. let me go to the test file. So a statement, for now, let's say there's two types of statements. Print statements and assignment statements. So, and print statements, just because we don't want to deal with general function calls for now, these are just hard-coded to print stuff so we can see the state and the intermediate state of different variables. And then assignments, I guess like, yeah, assignments will be like x equals whatever. And they will be terminated like that. So I guess we need to extend the parser. By the way, one thing that's a little bit unusual here is that I'm recognizing local versus global at the token level. That's not something we're going to keep in the final compiler. It's just a convenience for now. So yeah, token, I guess this would be like, well, semicolon will be single operator. I guess we need a token print. And actually, we won't even have token print. Token print will just be P. Let's just do single characters because we don't really, I mean, I don't want to have to start. I mean, it's not hard to parse multi-character tokens. It's just not the point, right? Like, so, oh, I don't think we need this here. Okay, so what other single character things do we need? We need P. We need equality. And we need semicolon. All right, so if current token is P, then we have a print statement. Then we parse an expression. Otherwise, we parse an expression as well. Actually, we don't parse an expression. So if you have a local variable, then Do I really want to call printf? So I guess with printf, argument 1 is RCX, as that's the pointer of this, and RDX would be operand result. Okay, let's just leave this for now. Let's do assignments. These are probably more interesting anyway. So once we've parsed an expression, all we have to do is, for local variable, well, what do we do for RBP stuff? Maybe this doesn't exist. Alright, there's only the sign extended move. Well, let's just use that. Does anyone have odds on whether this will work? Okay, it worked. Okay, that's not right. Oh, it's because it should be a displacement, not an indirect. So like this should be D, and this should be D. In fact, I'm surprised that didn't assert, but that's because we didn't have enough variables in play. Okay. So that is correct. That's how, like, when you set things up right, this is how easy it is to do new things. Like, we just wrote statements with assignments for both global and local variables in, like, was it 5 minutes? So, it's pretty good. Does anyone have any questions? Otherwise, I'm just going to plow on. Oh, you like my commit messages? By the way, the only reason I'm even using source control for this is because Visual Studio's undo keeps fucking me. I had to rewrite a function last night, and that terrified me. So now I'm just using it as a way of doing permanent saves. So I don't really care about the commit message. You can see these awesome commit messages. So you're asking about precedence parsers. I mean, precedence parsers refers to pretty much anything that does operator precedence, right? I know about Pratt parsers. I think they're pretty cool, but the one I consider the one that for me is like, why would you not always use this? Is this one? This is the one I'm using in my code. Precedence timing. And long before I knew what this algorithm was called, this was the algorithm that I guess had picked up somewhere when I was a kid. It's so easy to do it. It also works not just for handwritten parsers. If you want to do table-driven parsers, where you have tables that describe the different operators and their presence and associativity, you can write it like that too. Like the way they're writing it here is kind of more like data-driven, table-driven, whereas the way I wrote it in my code is just with manual, functions for each level of precedence, like one for plus minus, one for times divide. Regarding Pratt parsing, if you is it F but part Pratt parsing, the only this one, the only really good article I know about this stuff is maybe no, this does look like so this is Pratt parsing. I would suggest this article if you want to know more about it. I know that there's another article by what's his face, Douglas Crockford, on Pratt parsing. I don't think that article is any good. I mean, just in terms of exposition. I really like this article here. It makes clear this whole notion of the fact that there's a left denotation, right denotation, and null denotation that's associated with tokens, and he does it sort of polymorphically using these methods, but that's sort of a detail. But I like this article, but I still consider the technique sort of a little weird. I think the handwritten precedence climbing approach is generally preferable. I haven't really found a case where I wanted to use this over over my usual thing. Okay. Okay, what to do next? I guess control flow. We haven't done any control flow. And now that we have statements, that sort of becomes pertinent. Okay. And control flow is a little bit interesting because you have to do back patching or something like that. Alright, I guess let's do control flow. Let's just do if statements to start. I think again we'll do like if expression I and then expression yeah, so we'll do something like this. Actually, let me abstract away a little bit so that we can go back and replace later. Oh, too much trouble. Oh, I see. Yeah, that's probably true. Okay. So for an if check, the essential thing we have to do here is let's see. The essential thing we're going to do is it's essentially just skipping a block of code selectively if that thing is not logically true. So at this point, we know what the operand is. And So then we have to emit a comp, and right now I don't have. I guess we have to go and add those instructions. Okay, let's see here. Register. I guess let's do that one. And then we do a jump, not 0. Or wait, if this is 0, then so what I'm going to do here is basically some of these instructions that require backpatching are going to write out the address where the immediate is. Actually, I mean, I don't even have to do that. What am I talking about? Typo in expect token after I. Oh, I see what you're saying. Yep. Right, so we emit that, and we just do a temp destination, and then we say jump address or jump offset address is So we assume this is a small enough offset. Okay. So there's probably like an off by 1 or off by 4 or off by something in this difference calculation. But the basic idea is we want to selectively skip this statement block based on the condition result. And we don't know how much we have to skip. Since it's a one-pass compiler, we don't know how much we have to skip the first time through. So we just write out a dummy immediate operand, but we remember what that address of the immediate is in the code buffer. And then when we've actually parsed it, now we go back and actually write it to be the right thing here. So an example of that would be if we don't actually have relational operators, but so it's essentially just checking for non-zeroness of these arithmetic expression. But let's do like if this is 0, then do this, and in here can be like a equals y divided by something. Okay, current token was not expected. Oh, I see. I guess we can do it like that. Basically, ifs don't need semicolons after them, just like in C. Okay, that worked, or at least it ran. Let's see what happened here. So it's jumping to this. Well, that's definitely not the right target. So let's see, how long is this instruction? So I was... Or sorry, 2, not 4. So I was jumping to 2D, which isn't even a instruction address. Okay, let me see if I can figure out. I don't remember even offhand what the relative encoding is based on. Like, is it at the beginning? Is it based on the beginning of the instruction or not? Is encoded as a signed 8-bit, which is added to the instruction pointer. Added to what instruction pointer? I'm assuming the instruction pointer as of the end of the instruction, so that would be this, or not. Yeah, the end of the jump, you're right. So for this one, it would be... Actually, the easy way to do this is to do... So it writes to A. Yep, so that's correct. So if I now write to C with 42 and run that, this goes to 37, which is here, and here it writes to C, which is offset 16, so that's, okay, that looks good. Okay, that is ifs. Like if you want to do else, you can do that too. I see. So if there's an else block, then we have to emit a jump. I think the jump is just, yeah, it's just a normal thing there. So then we just do a jump. Of 0. No, that's not right. So let's see here. So now that we're doing else's, if there's no else, then we go there. Otherwise, let's see. So that's the same in both cases. Now, if there is an else, then we go here. Otherwise, if there's no else, yeah, so it's actually the same in either case. I see. Okay, now I'm good. And so we basically have to do the equivalent. Once we're done with this, we say else jump, end of else jump. Does parse expression ever emit bytecode at the moment? Sure. I mean, that's what it does. Well, it doesn't emit bytecode, it emits x86 code. I mean, almost all the code in here is from expressions, right? Um, function calls are not a problem. I mean, the only problem with function calls is observing the x64 calling conventions, which are a little bit weird, but not inherently difficult, and certainly not a difficulty for the overall scheme we're using. No, it doesn't defer it. It only defers things it can defer. So, for example, um, if a case where it will completely defer it is if it can do constant folding. So if you have an expression that's completely constant and there's relevant constant folding rules defined, then it'll get folded at compile time down to a constant and no code will be emitted. But if there's anything involving, for example, local variables, then that will always emit code. Anything that can't be folded. So it's not, basically anything that you want, you can have emit code either by necessity or because you're not folding. So if you have function calls, they would always emit code. So the deferring thing is selective. It's only when you want to. It's not everything that's deferred. Okay, where were we here? And then emittus register means basically, like the way I think about emittus register is as it ensures a post condition, right? Like the post condition is, and I didn't write it because it's almost self-evident, is like, hey, the caller wants this thing to be in a register, so if it's not already in a register, then allocate a register and move it to the register. So for example, if operand is immediate, then emit move to register is going to actually do a sign extended move to that register from the immediate. But generally speaking, you only want to call this when you need something in a register. So for example, if you're trying to generate an instruction that has an immediate addressing variant, you don't want to do a emittus register on that because then you're sort of inefficiently using the addressing modes available. But yeah, so not going to digress too much into that. I think I talked a little bit about it yesterday, but that's the idea. So okay, so let's see if it still works. So I don't have any else's right now, and it should just do what it used to. So it checks if this is 0. If it's 0, then it skips to 37, which is right after the assignment to C. So that's good. Now suppose we have an assignment to B. Okay, this is probably another case where oh. Yep. Okay, that worked. Okay, so now if it's non-zero, it shouldn't skip everything. It should go to the else block. Okay, so there's a bug here. This isn't off by 1 because of okay, so now it goes to 3D, which is after the jump. Yeah. And then this should just fall through because it's an else block, but this one then goes to 50, which is right after the store to B. So I think that's right. I guess we can also do while loops since we're going crazy here. Okay, so the idea with a while loop is that there's a header, and we have to evaluate that header every time through, and then we have a body and the body. Well, there's two versions you can do. You can either, since the general let's do the fancy, the one that assembly programmers do if they're trying to be semi-efficient, which is the check is actually at the bottom so that there's no unconditional jump in the common case, because you expect the loop to execute more than once. That's a reasonable expectation. So, so actually the very first thing you're going to do is emit a jump. No, why am I doing that? So the start jump is there. The start jump immediate. Immediate address is there, and then so we regenerate. No, that doesn't work actually. I can't do that in a one pass. Oh, that's annoying. So I can't do that in a one-pass compiler because it wants to emit code at the top because of the parsing order. So yeah, we can't do that. That's fine. It's not too big a deal. So anyway, we have to get the while header address. Then we emit this code. And essentially we have to do the same kind of stuff we're doing before, which is emit a comparison. and then skip this. Let's call this condition address. And then we will call this we parse the block. We then have to emit a jump, a backwards jump. So the backwards jump will go from the current address, this will now be negative, to the while condition address. And once we've done that, we will then backpatch the end of while jump address to point to let's just read this. So we record where the initial address is before the condition. We parse and emit code for the conditional expression. We make sure that thing is now in a register, if it isn't already at the end of that parse expression. We do a comparison with that expression to 0. If it's 0, then we skip, but we don't know where we're going, so for now we just record that. Then we emit the code for the statement block. At the end of the statement block, we jump back to the start. And now that we're at the end, we can patch up the address. So for example, we should be able to do while x plus y say c equals c plus 3 or something. And actually, I'm just going to move this afterwards so that we can see where the code is, namely at the top. Okay. So we do a comparison of RCX with 0. If this fails, in other words, if it's 0, then we jump to 2a. And 2a is after the jump. And this one goes back to the top, so that looks weird. This should be a jump. Probably because I'm doing the math wrong with this. That shouldn't matter, should it? Oh, it's so that's off by 1, but at least it's in the ballpark now. Yeah, oh, I just noticed. Oh, this has to be plus, I think 2, right? Next code, 6. I think jump. 1 byte. Well, we can actually just see it here. Let's see. 1, 2, 3, 4, 5, 6. Yeah, I could do the same thing, but let's just do it that way. Okay, this is not right. Next code. So at this point, yeah. Okay, maybe we'll just do that. That's more consistent with the other stuff. Okay, so that works now. So yeah, I think that means we have the whole suite of control flow primitives. So Angus asks, how hard is it to do a simple linker that can bring in import libraries? With that and a basic Axis shell, you can get the window API going on in this. Yeah, so I think what I'm aiming for at the end of today, and I guess we have another, maybe I'm stopping at 6, so maybe another 2.5 hours. But anyway, my plan is to basically do this as a JIT, so it will emit things into memory at with whatchamacallit, like with fixed addresses for the section, so you don't have to really do relocations. For import library stuff, I think the correct way to do it for a simple thing like this, that is not loading off of disk but is being generated into memory, is to just use get prog address, and then you can just call through those function pointers directly. So at that point, the main thing you have to do is calling conventions. So I don't think I'm going to do the exe shell. I'm just going to do, yeah. One character names. Okay, so they're making fun of my parser. I mean, I can go and do a proper parser. It's just not very interesting. Sure, but you can like I mean I'm basically setting this up as a JIT compiler, right? Like it's generating stuff directly into memory. Um, so just because I don't want to deal with all the PE wrapping and linking stuff, um, maybe that's a fun topic in itself. But so actually, let's do some benchmarking before we move on. Obviously, this is not what most people would consider a full compiler, but it would probably be interesting to see how fast this will go. Um, and maybe I can do some basic profiling if there's something really stupid I'm doing. Um, so the only thing that can be deferred is things that are side effect free. So there's no point, like the things that the only time when things will be emitted is if they're either side effect kind of things, and right now that includes anything involving local variables or global variables. Um, so yeah, I mean, let me post up the code to GitHub just so you can read the code at your own leisure because you're probably only seeing snippets on stream. Um, but it should be pretty clear just by thinking about what's going on there, how that actually works. The point about expressions is there's a lot of stuff you can defer. Deferring it doesn't mean, I mean, A, it doesn't mean it doesn't happen, but also there's some things that don't have to happen, right? Like if a parse expression, like what's an example? Consider in C you can do something like this, right? Like that's a valid C expression. In fact, I mean, I think maybe the compiler will issue a warning if I do this. Okay, so it won't even do that. But consider something like this, like a statement expression, or an expression statement rather. In this case, it doesn't have to emit anything. And in my system, it wouldn't. Yeah, this is C++. Or C. Well, it's C++-ish. It's mostly just pure C. What was I? What train was? Oh yeah, I went to benchmark stuff. So that's a million lines of code. Yeah, so that's around 12 megabytes of code. My code buffer will definitely be way too small, so let's just allocate a gigabyte. Let's see how quick that is. This is going to be slow the first time because of disk cache, I think. And also, we can't separate out the file I/O cost from the parsing cost because I do file memory mapped I/O. So let's see what this does. Oh. I wonder if that's true. Can I really parse a million? Can I compile a million lines of code in 0.1 seconds? That's pretty good if so. That's fucking ridiculous if I can do that. All right. Okay, Visual Studio is trying to auto reload the now disassembled mega program. I'm telling you guys, one pass compilers, they're fucking fast. Okay, Visual Studio is just shitting itself. The disassembly? Yeah, let's look at that. The disassembly is what? 230 megs. Good stuff. Okay, let's make it bigger. Um, I wonder why it's being so slow now. So it's still running in the background in case you guys can't see. I wonder why that got so slow. Oh, debug. Yeah, so that's 1 second. Pretty fucking good, if I do say so myself. And this is without even optimizing anything. I'm just going to post a humble brag on Twitter about these numbers in case. Let's see, how big is this? Yeah, Turbo Pascal. Dude, Turbo Pascal, like if the world could go back to the way it was when I was 13 and Turbo Pascal 7 ruled the world, I would be a happy programmer because for me that's the best programming experience I've ever had in my life. Um, there's actually a really interesting talk or conversation or whatever on Channel 9 with Hannes Habsburg recently. And he was talking about how kind of modern compilers are versus the kind of Turbo Pascal style compilers he wrote. And I kind of wanted to tell him, man, a lot of the fancy incremental parsing stuff they have to do with modern languages, like the new Roslyn compiler for C Sharp or the TypeScript compiler. I think the stuff they're doing is actually pretty cool. And in case you guys haven't looked at the incremental parsing and those compilers, it's very interesting. You should check it out. But if you could just do things faster without doing things incrementally, a lot of that stuff would be obviated. So I often wish that things would be done a little bit more like that and a little bit less than how they're currently done. I'm curious, like how many of you guys on the chat were around back when Turbo Pascal was a thing? Like I wonder if that whole experience is something that people haven't even heard of who started programming a little bit later. Um, but Turbo Pascal was this, like, let me see if I can find some screenshots. I think the first version I had was 6, but 7 was the one that, oh, how Danish you are? No, I'm completely, ja, fra Denmark. Oprindeligt fra Randers. Okay, yeah, Turbo Pascal, this was so good. Like a true integrated development, like I think probably maybe not probably not, definitely not the first IDE in history, but considering you know it was extremely fast. It was really cheap. I'm trying to remember what the initial pricing was, but it was like $100 maybe. Oh, yeah, $50. That's ridiculous. So Tom says he prefers Turbo C++. I remember Turbo C being pretty bad, but maybe I'm wrong. It was certainly faster than Borland C. Um, I think Pascal is just a better language than C, honestly. Like, well, maybe not original Pascal, which I think didn't have pointers, but Turbo Pascal was like a real systems programming language, and actually, arguably, um, no, you're high, Tom. Like, Pascal is awesome. Turbo Pascal is awesome. Turbo Pascal had you can do allocs in Turbo Pascal, couldn't you? Maybe I'm wrong about that. I mean, you can. I guess you can write your own heap manager if you want. Oh yeah, I remember this page. I'm not sure if you guys have seen this page. This is someone who disassembled the TP3 compiler. And I think you'll find that the approach he uses is very similar to what I'm doing probably. It's certainly a one-pass compiler. One of the things I really liked about Turbo Pascal was it actually had really good integration of inline assembly and other low-level things like that. I guess maybe Turbo C had too, but I just remember that specifically being very nice. Like, at least among the group of friends I grew up in where we did Turbo Pascal programming, I remember, people would just naturally switch to assembly anytime they needed something. It wasn't like a huge barrier. It was very nicely integrated for the time. And also, in modern times, doing like a one instruction inline assembly block is kind of a nightmare for performance because the compiler has no idea what's going on in there. But back in the Turbo Pascal days, nothing, the compilers didn't optimize anything anyway, so there was really no kind of transition cost from having small inline assembly blocks. Oh God, the GCC, what is it, clobber lists. This is the worst shit ever. I I often think that there's like the people that kind of grew up in the Unix world with where assembly was this like horrible thing that no one ever wanted to use. I blame this kind of shit for that. In the DOS world, your language was a means to an end. Uh, you you ideally didn't want to write assembly if you didn't have to, but it certainly wasn't this big scary monster. So you would just use it when you had to, and the language made it easy. I'm just gonna go grab a drink. Yeah, no, this is a compiler. If you want the source code as it stands, I posted it earlier here. So you can go read everything there is there right now. Oh yeah, let's finish the Turbo Pascal nostalgia trip. So I see two different ways we could go. We could start doing functions, or we could start filling in the type system. I think the type system is probably more interesting because there's some interesting code generation tricks that I kind of alluded to earlier, where you can do folding on the offsets, so that by the time you have to say load from a field of a struct or something, you don't have to kind of do multiple instructions to do the address generation. You can just sort of do it directly in the addressing mode of the target instruction. Yeah, something about Danish people that causes us to keep creating new languages. I don't know if that's a good instinct because Bjarne Slaustrup is also Danish, and that's probably the worst programming language ever created, at least with wide adoption. So I'm pretty embarrassed about having that dude be Danish. But then we have, I think Anders Hallsberg is actually like legitimately like, you know, I'm not personally like a huge object-oriented fan, but even going back to the Pascal and Delphi days, he certainly did it in the way that I find most palatable for practical programming. And the Turbo Pascal was amazing. I actually think C# is really good for what it is. I mean, there's a lot of basic premises you can question, but for what it is, it's pretty well designed. So Caleb is asking, how do I keep track of which registers are used at any given time? So right now we only do register allocation for expression temporaries, right? So when you're dealing with a complex expression like this, you have to store the intermediate results. And the good news about expressions for register allocation is that the lifetimes are extremely simple. They're kind of nested, recursive, tree-shaped. So you don't have fancy liveness patterns to worry about. And so because of that, I mean, I can show you very simply, but basically parse expression. These operands basically represent intermediate results or data or something like that. And when we allocate, when we have one on the stack, initially it's just an empty thing and it gets filled in over time. And actually, this is a little bit dangerous. This should be operand null. I hadn't considered that. No, that's actually not possible. It's always going to get filled in. So, but anyway, this is essentially how it's done. The leaves of the call tree will eventually decide, oh, I need a temporary register for something. Then it will call the function allocate register, and then you will do this free operand thing when you're done with the operand, which will, if the operand is allocated to a register, it will free that register. And so ultimately, this just boils down to having a bitmask that tracks which registers are available. And allocate register tries to find one and hands it out. Free register puts it back in. So Angus is asking, like, basically, how far can you get with this one-pass technique? The stuff you can't do very well at, you can't do good register allocation. You can't do good, yeah, instruction scheduling is definitely out. Also, register targeting, which is not quite the same as register allocation. Like even for here I'm doing register allocation for expressions. You can do better than I'm doing for sure. If like for example, if you have an expression that you know you want to put in AAX or something, you can probably do that better in a one-pass compiler than what I'm doing. Right now, I would use a temporary, probably a little too frequently, and then move it into say RAX. But yeah, register allocation is a big limitation. Um, the there's inherent boundaries to what you can do with this technique. However, so I'll say a few things. The first is that going from a one-pass compiler to a two-pass compiler already gives you a lot extra. And so even though I'm showing things with a one-pass compiler, there are a lot of techniques that transfer over to say a two-pass compiler. So for example, suppose you do a two-pass compiler that goes through an abstract syntax tree. By the way, if I was writing a real industrial strength compiler with this overall approach, I would do a two-pass compiler. I would probably not have an intermediate representation beyond an AST. The AST is really nice because it means you can write tooling that hooks into the AST. It means that you can have stuff like you don't need to have 4 declarations of functions. It also means you can do some kinds of register allocations in the first time pass. So for example, as you're constructing the AST in pass 1, you can record basic information that requires look ahead in terms of like register usage. So for example, if you find that a local variable is used a lot inside a loop, you can create you can increase its weighting, and then when the subsequent one pass through the tree does code generation, it already has some of that aggregate data to work off of. So yeah, I think for sort of a modern compiler, you can get really far with 2 passes. But compare that to like a modern compiler, which, forget about how many intermediate formats there are in a modern compiler. It does many, many passes locally through, for example, a given function. So if it's generating code for a given function, it's going to do probably dozens of passes on basic blocks or control flow chunks of a control flow graph. So like a modern compiler is like, it's not even like 5 pass or 10 pass, it's like dozens and dozens of passes. Not over the entire program in a linear order, but like over pieces of the program repeatedly. I think with 2 passes, like actual 2 passes, you can do a really good job. But yeah, modern compiler techniques, I think the cost is that the compilers are usually super complicated and also pretty slow. So what I would suggest, so here's my mental plan for a language compiler that I want to, maybe this will grow into that eventually, I don't know. But 2-pass compiler with AST as the intermediate format, and basically the second pass that actually just code generation essentially does what we're doing here, but rather than doing parsing, it just traverses the tree. And it will have a little more data from the first pass in terms of register weightings for local variables and stuff like that. And then you will have an optional LLVM backend where basically the AST can translate into LLVM bytecode or bitcode or IR or whatever you want to call it. And you can use that, but you will still have a fast one-pass compiler for day-to-day work. So if you do that, then suppose you can get within 2x or 3x for a lot of code. I still think it would be extremely useful to have that. There's a lot of code. Oh, and the other thing I should mention is there's a lot of stuff you can do as a user to write code that's more easily optimizable that people don't normally do because they know the compiler will help them clean up after themselves. People didn't used to write code like that. Like back in the Turbo Pascal days, people kind of had a very clear mental model of what exactly the compiler did and did not do for them. And they would automatically, for example, they wouldn't necessarily expect a compiler to cache, like it wouldn't expect the compiler to do alias analysis. So for example, if you're doing, like I actually do this a lot in this code, and maybe I'm even wrong sometimes, but like, yeah, like consider stuff like this. I read through the operand pointer here, and then I do it again here. The reason I'm doing that is because I don't want to have temporary variables for no good reason. This will force a reload unless the compiler can prove that nothing in between the first reference and the second reference will write to memory that is aliased by this field operand register. So modern compilers will do stuff like that, and it's really nice. But back in the old times, we wouldn't expect the compiler to do that. So we would just do, this, and then, do like that. And honestly, even in modern times, if you rely too heavily on things like alias analysis, you're going to be disappointed a good fraction of the time. And I know that for someone like Mike Acton, for example, rails against people who rely too cavalierly on register or alias analysis, and sort of like, hey, put it in a local variable if you want to actually make sure that things don't get reloaded. So if you don't expect compilers to do stuff like that, you can have it generate code that's pretty competitive without too fancy code generation techniques. But yeah, the big things you can't do are really fancy register allocation, instruction scheduling. I mean, I'm not really an expert on optimization, but my sense is that instruction scheduling is not as important on something like modern x86 as it was earlier because of out-of-order execution. Now, that said, it doesn't mean that you still have to have, that only works if there's parallel work, like if there's instruction level parallelism available to have the CPU have something else to do while, for example, if you're someone was mentioning this a while ago, but suppose you so with this technique, suppose that I actually continue to not do any register allocation of temporaries, so that they always go through this addressing mode. In that case, it's really important that I can cover the latency. So for example, in this case, I load from this thing here. Now there's 4 cycles of latency before it can execute this thing. And now there's a jump. So in this case, well, it's at the beginning of the code, so there's really no way it could have cached the result earlier. But in general, if there's a way you can get some independent dependency chains going, then the scheduling is not too bad. And what you can do with scheduling, of course, is you can bring parts of the dependency chains earlier, so they're available for execution earlier, rather than being too far ahead in the code stream for the ILP window to overlap it. But anyway, I suspect that there's probably, you can get within 2 or 3x, and probably even 2x for a lot of code, if you write the source code a certain way rather than write the compiler a certain way. But yeah, so Caleb is saying it's a good idea to always look at the assembly from the compiler. I agree. I mean, you should do that, and that's a habit that I think not enough people have sort of in their daily habits. On the other hand, if you're working on a 10 million line code base, and especially if it's template heavy, you know, it's 10 million lines time whatever the bloat factor is from templates. It's extremely hard to stay on top of things. Um, Whereas if you have a simple mental model of what the compiler does and does not do for you, you don't have to look at every instance of the compiler generating code. You really just need like a coherent mental model and apply it when you're writing code and reading code. You don't have to look at the assembly as much. But I mean, the ship has sailed. Modern compilers will do crazy things, and that on average probably do a lot to help you, but makes it a lot harder for you as a programmer to have an idea of what the fuck is going on. All right, what should I do next? Um, I don't trust compiler to pass SIMD registers correctly. I mean, yeah, like the standard calling conventions don't do anything for SIMD. You have to, oh yeah, vector call. Well, I mean, I think the compiler is actually never allowed to pass them. Like vector call is a different calling convention, right? So unless it can inline, it can't do anything. It's not even allowed to. Like the whole point of calling conventions is to serve as a consistent interface so that if someone has a library they're calling into, or someone gives out a function pointer, the recipient knows what to do with it. So that's not something the compiler is really like. The compiler can't change calling conventions willy-nilly for anything that's sort of like globally visible, and even for things that have like internal linkage. Uh, it's yeah. I mean, in theory, it can lead to a lot of gains, but it definitely complicates things for the compiler. I don't think any of the standard C compilers do fancy custom calling conventions. Right. So I know, but they don't. They only pass floats in the SIMD registers. They don't pass, say, vectors, right? Um, like the biggest quantity that the x64 calling conventions, like standard call or fast call or whatever they're called, will pass is an 8-byte quantity, right? Whereas that's only like 16 bytes is the actual size of a SIMD vector, or an SSE vector rather. Okay. I think one thing I will do is so right now I'm using these displacements to address global variables, but actually I think I want to do rip relative code. And basically the code buffer grows downwards and the variable buffer grows upwards, um, or something like that. And so fortunately I already did all this rip relative crap, so we should just be able to use that. Right, so for example in this case we want to do emit r rip d. So operand address minus code. Well, let's see. Does that work? So what is it saying? Yeah. Do we want to turn this into a 32-bit offset? No, it's the other way around, isn't it? It should actually be signed. No. So this is how far we are into the buffer. This is the operand address. So this looks more correct. modern compilers on x64 do rip relative addressing, right? That's a good point. Although the macro doesn't do that. So actually that's fine. It's not a it's a macro, but it's a macro that just pastes together functions. So this should actually be no, actually, I guess that's not true necessarily, because the same displacement could be passed in multiple. Well, it is only passed in once, but in theory it could be passed in multiple times. Yeah, well, I mean, it's certainly not a bad idea to be explicit about it. Actually, I should have a function for this. Get variable offset. Actually, I think this should be renamed emit operand to register. Ensure operand has register. Okay, sorry, just doing some local cleanup. So get operand address offset. And then we wanted to do that in other places. So this should be ribd get operand address offset. one downside of this is it becomes pretty hard to actually read. Or maybe not. Oh, this is nice. So the disassembly annotates the absolute address. And this also tells me that the absolute, well, there's definitely some stuff that's wrong here. So this is the offset from the current location to the beginning of the buffer. And then operand address starting at this location, right? Because by the way, in case this layout isn't clear, my idea is that there's code that grows like this, and then there's data that grows like this. And so the start of the code is the end of the data in some sense, or the beginning of the data, but in a left to right sense. Okay. I'm assuming that rip relative addressing, is it relative to the start or the end of the instruction? Like if it was a jump, then it would be relative to the end. And that's really awkward because we don't know what the end of the instruction is before we've emitted it. So Caleb asks, how hard is it for a compiler to try auto-vectorizing code that has a lot of branches? I mean, it's really hard. Like, there are general ways of vectorizing code with branches, but, you know, I assume that normal compilers bail out immediately unless they see some really simple branch patterns. Because effectively, you know, if you look at the way if you look at the way you have to do stuff with SIMD and branches, essentially you can have a fast path where that handles the case where all the different lanes take the same branch. And okay, yeah. So Mad Moose is saying rip relative is relative to the next address. That's a pain in the ass. Okay, I guess we'll just bite that bullet. Well, that fucking sucks because it means I can't do this simple thing I'm doing. I have to essentially backpatch. Actually, I can do a function to do that. Sorry, my wife just walked in. All right, where were we? Probably shouldn't be called that. It should be called patch last immediate with operand address. It's a bit of a mouthful, but I think it's fine. Let's see if that works. So the concrete artifact that should fix in the assembly code is that we should no longer have, like, everything should be consistent, regardless of the instruction length they're being referenced in. So 0 and 8. This one's wrong, I think. But 0 and 8 sound correct. But some of these are bogus. So this last one, well, so this is definitely wrong as well. So these are just simply not being patched, it looks like. So what was this being generated from? So that's an assignment. This is also a weird immediate. Oh, I see. The thing I'm patching is not the right thing. Oh, right, because I have to patch the displacement. I'm patching the immediate and I want to patch the displacement. The displacement comes before the immediate. Okay, what's the best way to handle this? All right, thanks for coming by. Okay, so these now all look like they have the right offsets, where previously they did not. So you can see that I suppose A is FE8. No, it doesn't look right. So there's actually some bogus code generation here. I wonder what introduced that. Maybe that was my, must be my, this thing here. Let's just try squashing it. Okay, so now we have good code again. Yeah, so that was definitely not. So when you have a displacement, the displacement comes last. So let's try putting it back in. But let's just disable them for these and see if we have good code gen. Now that actually doesn't make sense because the code gen fuck up was earlier in the stream, in the code stream. No, that does work. Is it a bad idea to defrag an SSD? I think so, yeah. I think the whole FTL layer is intended to do any remapping it needs to do, but traditional defragmentation, I think, is probably a terrible idea because it's going to create a lot of writes. And the way flash drives work is, or flash SSDs and NAND memory drive work is, you know, there's a general degradation over time with writes. And I don't think it really helps you. But I could be wrong. I actually don't know that much about it. Okay, so this looks good. So the problem is clearly here. I'm trying to patch the displacement. The last 4 bytes are here. I don't want to overwrite these. I want to overwrite the 4 bytes here. So what am I doing wrong? I see. This is the problem. Okay, I think that fixed it. So in theory, now that everything is RIP relative, we should actually be able to run this code. So far, we've only been staring at disassembly, which is fine and all. There's not much point in running it, honestly, until you're a bit further along. But I think now that we have these RIP relative ways of addressing global variables, we should be able to actually just do this for real. So let's do that. So instead of using the static code buffer, well, okay, let's think about what we're going to do before we do it. So we're going to do a virtual alloc of a very big buffer. And allocation type, I think we do mmcommit with read-write permissions. Let's make sure that works. We're in release, we can't see shit. Okay. Yep, that worked. So we get a big pointer, and then code is essentially going to be that plus, I don't know, how much, let's just say, so page size is this, so we're going to do that. Then we're going to virtual protect. Well, this is a commit. Yeah, I think a commit is fine for 1 gigabyte. So then we do a virtual protect. Let's see. Let's can find the flags. Actually, we can just, let's just make it all of it executable by default, so we don't have to manually slice it up with protection permissions. So I think that still works. Let's disassemble it and just give it a look over. That's good. We should now be able to this is the moment of truth. I think this is working. let's try that again. So the first variable is code minus 8. So I guess let's do something like x is 1, y is x times 3, c is y times y, and let's see what happens then. Okay, just step into this. Actually, I'm writing into the local variables, which are probably overwriting random crap in the parent stack frame, but fuck that. But anyway, I think I want to use A, B, and C. This is A, this is B, B. Stop. I keep trying to... If you do control... If you do step into, but you're not switched to assembly, it won't step there, so... which is not great. This is certainly not correct. I see, so it can't even evaluate these because, yeah, why can't it? That's weird. They're globals, right? Okay, it's a little annoying I can't have that active while I'm stepping here. So anyway, okay, so this loop is never going to finish, but I should be able to walk back up here and see the latest values. So this would be 3 squared, which is 9. So I mean, yeah, this code is executing. All right. I'm just going to comment this out. But anyway, the code executes, so that's great. And all the relative offset stuff is working as expected. Next step, let's see. I guess I can make sure I didn't make everything slower. Actually, let me just pull this up. It's going to be slow without debug. Yeah, so still around 1 second for generating huge bin. It should be only 1.0 once it's in disk cache, yeah. Okay. I should probably just delete this now. Okay. Does anyone want to vote on what we do next? My inclination is to do kind of proper user-defined types, and also just types in general. Right now, everything is a 64-bit quantity. So I think I'm going to do types. And along with that, I'll probably do proper parsing so we don't do all this single variable shit. The other option, I guess, is functions. I just did x64 calling conventions in a mini project I wrote on stream, I think 2 weeks ago. So that's pretty fresh in my mind. On the other hand, I think without interesting types, it's probably not too useful. Actually, though, before we go on, let's write a simple program that actually does something useful. Well, useful is relative. Let's do Fibonacci. I think we need a temporary for that. So let's use x. X equal to b. B equal to c. C equal to c plus x. And then a is a minus 1. All right, let's actually, probably the right way to do this is we say the input is in a global variable. Then we do everything with local variables. So c is equal to x, new x is equal to y is equal to old I plus c. And then at the end, we put the result if the result is now x. So it's something like this. Ooh, interesting. Why did that crash? Oop, I think I know. Oh yeah, it's already open. That was a typo. Okay. I guess let's try executing it. No, you can't really avoid having to pre-declare functions. That's just part of a single pass compiler, unfortunately. It's also why a lot of languages like C force you to do so, because they were originally written. Actually, I don't know if there's ever a true single pass compiler for C. Um, the Speaking of that, like, I don't know if you guys have seen this, Primeval C. If you go to this is Dennis Ritchie is unfortunately deceased now, but he wrote this before he died. It's a dump. It's about a bunch of background, but also some early C compilers. Before it was anything recognizable as NCC or even KNRC. But all of these are multiple pass. But a lot of those early languages kind of required that for declaration. Because I think, yeah, if they do type checking in the first pass, then you need 4 declarations. So, but anyway, so there's no good way to avoid it in a single pass compiler. That's part of the and I think I mentioned it earlier. One of the nice things about a true two pass compiler with an AST is that you can do things like, you can do forward calls without having to forward declare. So anyway, let's see what this does. Access violation. I think the access violation is because of the call frame. A dumb fix-up path. Yeah, I mean, the problem is you also don't know where the instruction pointer is going to be, so at a minimum you still have to do relocations. But I mean, you're right though. You can kind of, I mean, the way C actually works, right? Like old school C is that it could call functions without forward declarations, I believe, and it would just assume that they would return ints or something because they were using a pure stack convention, I believe. And unfortunately, it does. I think it does mean that there's like no type checking, right? And so if you read past the end of the passed in parameters, you're essentially reading into parts of the stack that are not intended for you. And so, that's pretty damn risky, even for a low level language. Okay, so where were we? Right. So I think what's happening, well, let's go. I think what's happening is it's trying to read through the frame pointer offsets, and the frame pointer isn't set to anything meaningful. Right, it's just set to 0. What we could do is we could set the frame pointer to the beginning of the code array. Okay, so that works now. That's a little too big. Let's do it with 5. What's the fifth Fibonacci number? Well, actually we can just calculate it as we go here. Okay, so now we're done. Should be able to go up. Alright, there's one more instruction we have to execute before things get written back out. Now we should be able to get back up and look at the Is that right? Fibonacci sequence. Right? 0, 1, 2, 3, 4, 5. I see. So if we do 6, 7, we should get 13. Okay. Yep. Best Fibonacci calculator ever. $55. Okay. That's all good. Okay, I think we should start doing probably types. The other nice thing about types is, well, before we have a way of actually declaring types inside the language itself, we can define them sort of by hand in C, and from there we can, we can kind of test access to those types. So yeah, let's think about what a type is. We have things like UN64, which is essentially the only thing we currently have. We have things like int64s with signed arithmetic, which mostly matters for multiplies and divides. What else do we have? Well, we have, let's just create the full matrix. Let's not do 16, but we can do 8. So these are the primitive types. Then we also have aggregate types. And we have arrays. If you have an array, then you will want to know array base type. And arrays, well, let's just call this base type. And then this will be array. We need the size. Or length. And if it's an aggregate, then we need a we need this. No, actually, we just need fields plain out. A field. For now, we're not going to have field names. We're just going to have logical indices. So then a field has, I guess, really just types. Now, let's fill in offsets. Let's make that part of the basic definition here. Okay. So the thing that's interesting about types from the code generation perspective is what happens when you have so-called selectors. So a selector is something like, you know, you have a person, something like this, and then you have an instance of that, and you say something like pair name equal pair age equals 33. If you think about what the code generator needs to know, essentially what it needs to know is like, what's the address I should be storing to? So by virtue of being a local variable in this case, although it could have been a global variable, but by virtue of having some address in memory, pair has its own base address. And then when we access a field, we effectively compute an offset address added to the base address from the struct variable itself. And arrays are basically the same thing, right? So for example, if you have, I guess we can take sort of a interesting example where we have an array of structs. If you do something like this, what you're essentially doing is you're doing this sort of offset address generation math at two levels. So first off, people is a object in memory. It has its own address. From that, we are now accessing element number 2, which means that we're essentially doing, if you were doing this in C, you would say you're doing this, and then you're adding offset of, you're doing this, right? That's essentially the calculation that's going on under the hood for figuring out where to store this 33 in this example. And the interesting thing to note is that while people may not be known, its address may not be known until runtime. Although if it's a global variable, it actually will. At least its relative offset, if you're using RIP relative addressing, will. All of this stuff to the right is actually constant, right? The size of a person is constant. I think in this case it would be 16 if it's 64-bit because of padding and stuff. The array index is known, so that's also constant. And the offset is definitely constant, right? That's just a feature of the data structure definition. So essentially what this boils down to is people plus, I guess we can do them, if this is 16, this is 32, 48, plus 0 for the age. So this is really just doing this. Something like this is what it boils down to. So from the code generation point of view, we would like to be able to do constant folding essentially on all this address offsetting crap. And, again, I learned these tricks many years ago from studying Niklaus Viet. Go read his books, study his code. But a lot of these simple sort of one-pass code generation techniques, including for things like arrays and structures, I pretty much stole from him. So definitely don't claim this is original, but it's a good, easy way of doing it in a one-pass compiler, or even any compiler, but especially useful if you're not doing fancy instruction selection or anything. But yeah, so I think what we're going to have is an operand. You know what? I'm going to rename operand type to kind, because operands will have actual types now. This is, by the way, also where we're going to do type checking. Because now operands, we were kind of using operands as a useful way to traffic around, data around where things were stored. But now we're actually going to associate types to them, which will also make it easy to do type checking. So, yeah. Maybe we should do some local variable. I should actually expand the parser to be a little more flexible at this point, I think. Because otherwise I'm going to keep running into these annoying limitations on what I can type. All right, so what would we want? Let's say that if you do this, then you declare a variable with that name and type. let me just think about how we're going to do this. So we declare variables like this. For now, let's just do variable declarations. So first off, I think I'm going to expand my definition. Rather than starting with a statement block, we should be able to, so basically in order to get the existing code to do the same thing, I think we will do something like this. So these at the top level have the meaning of declaring variables. And locally they have the meaning of declaring local variables. So global variables and then local variables. We might as well also make it work. Yeah, let's say we can declare them inline and they have scope over the consequent space. And for example, you could do something like, since we only need that here, we should be able to do this. And since we don't use C, we can just write like that, like that. All right, I'm just going to go to the bathroom and I'll be right back. All right, I'm back. Right. So let's do proper symbol tables now. This will also slow down the compiler, so maybe my benchmark figures from earlier will be a little more humbling. But let's do some symbol tables. I guess one thing I want to do. All right. So how are we going to do this? So we should have an overall string table, which is essentially just for interning purposes. And for now, let's not worry about growth. So we will have a hash function. And then we will have a flat list of hash strings. I see. So you mean that they hash it, but then they do early outs based on. Yeah, maybe we should do that. That's actually not a bad idea. Um, Okay. Um, hmm. So actually I should make sure that this never happens regardless. And we will probably have to revisit some of these things in the process. Do we really want to do that? It's going to drive me crazy. I mean, it's a jump table, so you kind of want to be able to do this. Man, I wish C just had like you can do ... on cases. Okay, let's do it. Actually, let me let me see if I can find a someone who's already written that out. No, hang on. Let me just write it here. Um, um, what is it? I don't have Python installed. Okay. Mm, yeah, let's just do that. I mean, I could do this as well. don't think you don't need to compare the hash when you already have the intern pointer. So intern string start n minus start. This is probably not the fastest thing ever. Like if you could discriminate based, well, actually let me just do it. Let me just do it this way. Yeah, no, I know it's not used for keywords. The keywords, this is just my lazy way of handling it. I'm going to use it for both. Okay, what hash function should I use? Maybe just good old fnv hash. So fnv hash, there's an fnv prime, an fnv initializer. Maybe some initializer here. And that, I guess the prime will be whatever, and then the initializer will be whatever. The f and v hash is by no means the best hash function ever, but it's the shortest hash function I can write. That's not complete garbage. Alright, so we're just going to kill these. Okay, so now we've interned strings. Okay. Better hash function. God, what was it? When I worked at Rad, I mean, there's a bunch of. Well, I don't think I can say this was my bad code. I think it was someone else's. But there was some. Fabian was doing an investigation. I'm trying to remember what the context was. I think we were hashing pointers. And anyway, the hash function was basically like when you looked at the distribution of the hash values relative to the range, they were like not even hitting. Like, a bunch of their bits were always 0 or stuff like that. So you were like using a fraction of the range. Um, if you're writing hash functions, and you should really like look at actual distributions and stuff for both random and, well, actually random data is the only. I think this is the standard problem that people run into. Any hash function that's not like literally brain dead will work great for random data, because random data will work great with, even a function that does a pure modulo with nothing else is fine for that. Because the randomness is already in the data. The thing you want to do is you'd want to take data that's kind of correlated, and then you want to decorrelate it. But, you know, it's so easy to just generate random test data. That's what people tend to do, and I do too. So, anyway. Okay, so we need symbol tables. And we're just going to use flat lists again, because why the hell not? So a symbol is going to have a name and a type. In addition, we are going to have some local variables. I need to make this something big as well. I think the difference is with local variables, well, so first off, this is a symbol, and then you need to know whether it's local or global. So They're actually both offsets. Let's just call them that. And we can just call them actually offset and rely on the enum to disambiguate what they mean. For local variables, we're going to have this sort of stack discipline. Can't really do that because type is not defined yet. Well, let's go to type. Maybe not count, maybe index. Meaning when you leave a stack frame, so when you enter a statement block, it's going to remember how many local variables were on the scope, and then when it finishes the scope, it's going to sort of say pop back to that, or so maybe calling it pop is not the right one, or reset local variables. No, let's call this like new count. So that I think is pretty tough documented. So essentially all we do then is just do this. I think that's actually all you have to do, right? No, that's not true. You also have to set the offset. New count should be well, if let's see, if new count is 0, then the new offset is 0. Otherwise, we have to go, let's do it out here. Let's see. So we also need something equivalent. For push global variable. Now this offset, I guess, goes in the other direction. Although we can just count up and then yeah. I think push is good. We should also create some Okay, finally we can start rewriting this crap. So if we now have a token identifier, then all right, the other thing I didn't do, push local variable, find symbol by name. Unfortunately, because these are interned, we can just do pointer compares, which is beautiful. We have to do these back to front, back to front, back to front. Okay, the thing I want to write is, okay, let's just do it like that. So why does it look broken? Oh, I see what you're saying. It's the ordering. So what we want to say is, if the new count is less than the thing, then we update the offset to sort of point where that was, or the. I think that's right. So what were the initializing truncation of constant value? Actually, let's just leave these. Okay. So right now, if I try to compile Fibonacci as an example, it should assert on not finding symbols. It could assert sooner. Okay. Oh, it's release, so it's not hitting the asserts. Okay, it's actually asserting even sooner. So where are we? Oh, it's because I put a bunch of stuff in here that I haven't actually coded yet. You know what? Maybe I'll just code it right here. That's a good way to force myself to just do it. So I think the way this works is if we see an identifier, let's just save it. Then we do read token, which I forgot to do regardless, so that I think is a mistake. So let's do that up here. So now we've read the identifier. I think there's now two cases. If current token equals an assignment, then so let's also pull that out. Then we basically do all this junk. Else, we assert that the current token, and actually I have to go and add that. So then we skip that. Actually, I should do expect token. I shouldn't do assert. So now we're looking for a type. Okay, just lost my train of thought. So if we see a type, And for now, let's just assume parse the type. I think that's just going to return. So we're going to parse the type. And having parsed the type, I'm going to push a local variable. This means we need to make a function called parse type. For now, it's just essentially if current token is identifier, if current token identifier equals identifier equals string uint64, then return type uint64. Okay. So in theory, so that was for local variable. Let's also do global variables. So we will have a notion of a module, and a module while current token is not equal to the start of a block. So basically, this is how we're going to do. We're going to assume there's a bunch of an optional number of global variable declarations. Okay. So current token identifier is some huge monstrosity. Should probably verify that this thing does what it's supposed to, which seems to not be happening. current characters, remaining characters. So this is A. So start should point to A. Now we skip the A. We say, is the current character alphanumeric? It is not. End points. Yep, that points to the correct place. Let's go in here. So string has length 1. We go in here. We initialize the hash. XOR this in, do that, and now we're done. We go through these, none of these should hit. These are reserved words. Oh, here we go. That's the problem. I can't use stir dupe. Actually, let me make that faster. Next, oh, I see. Okay, still get an error, but at least we seem to be further ahead. Parse module. Current token is F. I don't even think there's anything called F here. Oh, let's just single step from the beginning. Oh. What fucking module are we parsing here? Oh. $28, $29, $30, $31. feel myself getting tired now, because this is the kind of stuff that should not be. Oh, I know. Or I think I know. So anyway, none of these are hitting. I'm not incrementing next string data. That's definitely one problem. Maybe that is just the problem. Probably want to null terminate them just to be nice. Otherwise we can't really inspect them very well in the debugger. So copy the arrow and overwrite it and increment this. Okay, at least we're now further along. Okay, so let's see why parse type is not returning anything useful here. UN60, oh I see. It's because I'm not doing this. Oh, I never interned UN64. Okay. I know. Getting tired. So identifier is A, and it's trying to find it. And where are we? A equals 10, it looks like. So we're trying to find it here, and it's not finding it. So, okay. Let's see why. So, trying to find A. What are our global variables? So, global variables count is 0. Probably. Okay, now we're dealing with a symbol that is equals. Somehow we made it all the way down here. That's interesting. Pretty bad about remembering to match up those probes with reads. So now we're doing, I guess, x equals 0. So we've done a equals 0, but so x equals 0 is this is an amateur hour shit here. So if we find this, I mean, I see what the problem is. Okay. No, that's not true. Why is that not? I can feel my brain turn to mush now when I'm getting caught up on stupid stuff. I think you should probably stop. I'll give myself a timer and say I'm stopping in 5 minutes. Hopefully we can fix this bug before then. So when we see an identifier, we get the identifier, read the token. If there is an equality check, we consume, or not equality check, there's an assignment, we consume the assignment operator. We try to find the symbol. After we found the symbol, now we have to then expect token identifier. I'm going to rename this to consume token. Oh, this is nonsense. What am I doing? It's already consumed the identifier. Now it's consuming the equality. And then this will, by itself, handle the expression. If you don't get a equal sign, then get a type. Parse the type. Create a local variable of that type. Oh, but this is only... So for global variables, we do this, expect this, get the type, push it. Okay. All right. Caleb's asking, what is string interning? Yeah, string interning is basically the idea that every string has a unique representation as a pointer. So if there's two strings with the characters I and F, right, like if, there should only be one in the string pool. There should be basically a pool where there's a unique representation of that. And so in parsers, for example, it's very convenient when you're parsing an identifier to intern it, meaning get back a pointer, either an existing pointer if it already exists in the string pool, or a new one if it just was created. And then that way, after you've done that initial interning operation, you can now do string comparisons using just pointer equality checks, which are, pointer equalities are basically free. String equalities, requires loops, can be arbitrarily long if the string is long. So anyway, it's like a standard technique, especially useful in compilers. Okay. It's funny, I've been doing these streams now, and I'm always able to tell, like almost like clockwork, when my brain turns to crap, and I am just literally unable to do anything, even the simplest things. And I think we've hit that point. But I would actually like to get this working, so I'm going to power through for a few more minutes. So we're expecting this. We have an open paren. The remaining characters are oh, I see. So we've actually made it all the way to here. So it was, so where are we? W. Oh, I'm an idiot. We actually have long names for everything now. Because it used to have these one character shorthands. Now we actually have something better. Okay. But at least it ran. Okay. Let's try to step into this and see if it... Yes! So this is 55 is the correct Fibonacci number, and we're now doing it without let's say, so we can even say this is like fit input, fit output, and this is fit input. Okay, let's go back up to the call stack and see what these are. 55, yeah, so that works. Okay, finally, so at least it was just a few stupid parsing bugs. The actual logic for, well, we haven't done pushing and popping of local variables yet, but we can do that next. That'll be really easy. No, actually, we do that. So for example, if I do this, I will get an assert. No? Okay, that's a bug. Because if I do this, I should get an assert because it's not in scope. Yeah, so that gives me this assert. So it actually means we're not doing the popping of local variables correctly because this thing should be out of scope by this point. So let's fix that. This is the one last thing, and then I think we are done for today. Okay, this is 0. And now we step over that. There's now 2 local variables. Actually, there's nested statement blocks, so I should. So this is the first one. This is the second one. We now have 2 local variables. If we run to here, we should have 3, and we want to pop back to 2. Two is less than 3. So this is correct. And now this should go from 3 to 2. Then I'm confused about why. Okay, so now we have the C, and we try to find the symbol. Oh, I see. Good old off by 1. Okay, so now that asserts, as it should. Otherwise, yep, just goes to the end. Okay. I think that's pretty good. So what did we do that we didn't have a few hours ago? We did global and local variable stuff. We did non-single character variables and symbol tables and string interning. And the local variables have proper scoping, like block, local scope, not just function scope. And we verified this code actually runs on the machine. and I think this is pretty good. One thing that might be interesting to see is how much slower this is than what we previously had. So I think I'm going to finish with that. So like huge fib b, and then this will potentially also expose other bugs. Actually, I think I screwed up. Let's just do this so it's easy to see the... So this is 4 million. So this is 10 million, roughly. Just say that. This will probably be substantially slower. Nah, it's not really. 1.1. In terms of file size, if you compare huge fib b to, yeah, so this is exactly as a little bit bigger than huge b, and it runs like a few percent slower. So, you know, that's still like 125 megabyte source file compiled in roughly 1 second, which is pretty good. All right, I think I'm done for today. Thanks for sticking it out. I don't know if this was interesting or not, but we're definitely making some progress. So tune in next time, I guess.